So now let's go into the discussion of the normal distribution, which is a very common distribution used for different models that you'll be doing later on. Sometimes the normal distribution is also called a Gaussian distribution. So if you've seen that in other literature, that is what that value is. The normal probability distribution has a fairly complex formula, but typically to find the formulas, instead of using the formula to find the probabilities, we're going to use either tables or a calculation in Excel. But some properties of a normal distribution is that it's going to be bell-shaped with one single peak in the middle. The mean, the median are going to be the same value. It's asymptotic, meaning that it never touches the x-axis. And there's a whole family of normal probability distributions that we can talk about here in a couple slides. But graphically, when we look at the normal distribution, you see that the location of the normal distribution is going to be determined by the mean, which is that center portion of your bell-shaped curve. The dispersion or spread of the distribution is going to be determined by the standard deviation. The area below the curve defines your probabilities, just as we had with our uniform distribution, and so the entire area under the curve is going to equal 1. So the area to the left of the mean is going to be 0.5, and the area to the right of the mean is also going to be 0.5. So there's not just one normal probability distribution, but a whole family of them. Our top left chart is going to look at the length of employee service at 3 different plants. Here, the mean is the same for all 3 of them, but the standard deviations are different. In the bottom chart, we see box weights for 3 different cereals, and the means are different, but they all have the same standard deviations. And then in the top right chart, we see tensile strength of different cables. We see that they all have different means and different standard deviations, but they are all still considered normal distributions. But what's most helpful about the normal distribution is we can standardize it. So the standard normal probability distribution has a mean of 0 and a standard deviation of 1. And so we can do a transformation on our data to scale it, basically to force our mean to be 0 and the standard deviation to be 1. And we can use this by using our z-score value, where you take your observed value minus your mean and divide it by your standard deviation. And so we can use those standard deviation values from a z-table to find the area under the normal curve. Because unlike the uniform distribution where you just do length times width to get the area under the curve, the shape of the normal curve, remember we said, has a little bit more of a complicated probability distribution function. So here, if we're looking at an observation that's 1.5 standard deviations away from the mean, here we're looking at grams. So we're looking at a distribution where the mean is 283 and the observed value is 285.4. That observed value is 1.5 standard deviations above the mean. And so when we look at the z-table, we go to z where it's 1.5.00 to get the area under the curve between 0 and 1.5 standard deviations being 0.4332. So let's look at an example. So here we're looking at Uber. For some of us, Uber is a little bit newer than for some other people. This idea was first developed by Uber Technologies, which is headquartered in San Francisco, California. If we have different drivers, we have a standard deviation of 100, and we have a mean of 1,000. So if we want to know what the value of a driver who earns $1,100, the z-score for that is going to be 0.1. Okay, and then we have what's the z-score for a driver who earns $900. So they make $100 below the mean. That's still going to be -1. And independent of the direction above or below the mean, the area of the curve is the same because, by definition, the shape of a normal distribution is symmetrical. So let's talk about the empirical rule. We talked about it a little bit earlier in the course, but to verify it, we can use this table to find the z of one standard deviation. And when you have one standard deviation, the p-value for that is going to be 0.3413. So what that means is the probability of observations falling between the mean and one standard deviation away is 34.13%. So going to the empirical rule, if we're looking at one standard deviation above the mean and then one standard deviation below the mean, we can add those two portions together to get approximately 68%. Two standard deviations is going to give us 95%, and then three standard deviations basically is, 99.7%. So practically all of your observations. So here, we can look at, quality assurance. So the Autolite battery company is going to conduct tests on its battery. And we want to know, so about 68% of the batteries are going to fail between which two values. So about 68% is going to fail between +1 and -1 standard deviation. Okay, so one standard deviation is 1.2 hours. So that means that my low end of that range is going to be 19 minus 1.2 hours, which is going to give me 17.8. And then one standard deviation above 19 hours is going to be 19 plus 1.2 to give me 20.2 hours. So using the same concept with 95% corresponds with two standard deviations. So two standard deviations above 19 is going to be 21.4 as my upper end, and two standard deviations below is going to give me 16.6 on my lower end. And if I wanted to say virtually all of my batteries are going to fail in what range, that's going to be my mean, plus or minus 3 standard deviations. So 19 minus 3 times 1.2 gives me a value of 15.4, and 19 plus 3 times 1.2 is going to give me 22.6 hours. So let's look at an example here. So we have, what is the probability that a driver earns $1,100 or less? Okay, so the first thing we're going to do is we need to find out the z value for a driver who earns $1,100. And so when we do that calculation, we see that the z value is one standard deviation above the mean. So when we go to our z table, the corresponding p-value that goes with 1 is 0.3413. But our question isn't asking what's the probability that a driver will earn between 0 and 1 standard deviations. It's saying, what is the probability that a driver will earn up to that amount? So we also need to include the other half of that normal distribution. So in order to get this final question saying, what's the probability that my weekly income goes all the way up to $1,100, I need to take the probability that they're going to earn between 1,000 and 1,100, which is the 0.3413, and then add it to the probability that they're going to earn less than 1,000, which is 0.5. So the final answer for this question would be 0.8413. So I have an 84.13% chance that a driver is going to earn $1,100 or less. So now let's look at another part. It says, what's the probability of a driver making less than $790? So here we're looking at that far left tail of our probability distribution. So when we do this, first thing we need to do is find the z-value of our driver to put that into terms of the normal distribution. We get a z-value of negative 2.10. Okay, so when we go to our z-chart for 2.10, we have a p-value of 0.4821. That 0.4821 is describing the area under the curve between the mean and my z-value. But we want to know the area just beyond that. So in order to find that value, we're going to have to take 0.5 and subtract that 0.4821 to get the p-value of 0.0179. So please remember, particularly with these z-charts that go from the mean outward, they are telling you the probability more towards the middle of that normal distribution. Here we have an example where we're combining two probabilities. What's the probability of a driver earning between $840 and $1,200? So the first thing we have to do is find the z-value of a driver who earns $840. And so we get a z-value of negative 1.6. And then the z-value of someone who earns $1,200 is going to be a z-value of 2. So now what we're going to do is we're going to look up on our table the area under the curve between 0 and negative 1.6, and we're going to get that the p-value for that is 0.4452. And then we need to look up the p-value associated with being at a z-value of 2, and the area between 0 and 2 standard deviations is 0.4772, giving us a total area of 0.9224. So I have a 92.24% chance of a driver earning between $840 and $1,200. So when we're looking at it like this, we're just going to add those two areas together. Now let's look at the probability of a driver earning between $1,150 and $1,250. So both of these are on the same side of the normal distribution. So when we get our z-value for $1,250, we get a z-value of 2.5, and $1,150 is going to be 1.5 standard deviations. And so now what we're going to find is that if we're between $1,000 and $1,200, $1,250, that area under the curve is going to be 0.4938. So between 0 and 2.5 standard deviations on your chart is going to be 0.4938. Okay, then we look up the p-value for 1 standard deviation, or sorry, 1.5 standard deviations, and that's going to give you the value of 0.4332. So the area where these two values don't overlap is going to be the range that we're interested in. So with these types of questions, I actually find that it's very helpful if you take the time to draw the chart and really emphasize to yourself, are you looking at where they overlap, or are you looking at where they don't overlap? Are we looking at what's closer to the middle, or are we looking at what's in the tail? So once again, I do highly recommend that you spend the time to draw the pictures and see exactly what portion of that graph you're looking for. For this particular question, we find that about 6% of our drivers are going to earn between $1,150 and $1,250 weekly. Here we're looking at a tire company where we're starting with trying to find that z-value that's going to give me that 4% in the tail. So if we know that half of the normal curve is 0.5, and my table is going to give me my area under the curve between my mean and my cutoff point, and I want the 4% to be outside of that cutoff point, we're going to do 0.5 minus 0.04, so we're looking for 0.46. So now what we need to do is we go into our z-table and we find 0.46, or its closest approximation, which in this case is 0.4599. That is going to correspond with a z-value of 1.75. So when we look at our table, we know that z is x minus mu divided by sigma. We don't know what x is, Our mean from our problem is 67,900 and my standard deviation is 2,050. And like I said, on the table, we looked up that value of being 1.75. We know that it's the negative value because looking at our picture that we drew, we're looking at it being in the left side of my diagram. So then when I substitute these values into my equation, I'm then able to calculate that my x value is 64,312 miles. So what this means is the minimum guaranteed mileage should be set to 64,312 miles so that only 4% of the tires will be replaced under this plan. Little bit of a review. Remember that our normal distributions need to be symmetrical, and so when we're talking about this, a lot of times you can have data that is sort of normal, sort of not, right? And so how much skewness is acceptable to still treat it as normal, right? So here we have a skewness of 1.25 and a skewness of 0. Typically, if your skewness is between negative 0.5 and negative or positive 0.5, it's fairly symmetrical and you can go ahead and treat that data as a normally distributed data set. If you have a skewness value of 1 or less than negative 1, that's going to be considered highly skewed and you're going to have to use either a transformation on that data or maybe a different kind of distribution for your variable. And so here is moderately skewed, so that's between 0.5 and 1 or negative 0.5 and negative 1. That's considered moderately skewed. Still a little bit, in my opinion, maybe a little bit too skewed to be able to continue using that as a normal distribution. So once again, if you have a skewness beyond 0.5, you might want to either consider using a different type of function or maybe even transforming your variable.